numerical problem 3, and I'm going to run for about, I'll aim for no more than 30 minutes, and then we'll have a break, and I'll be happy. We'll have a 10-minute break, and I'll be happy in that 10-minute break to answer any questions about numerical problem 2, which apparently has been causing some challenges. And then Said will take over and talk about sensitivity analysis and risk attitudes. Yeah, so I'll then help anyone who puts their hand up. Okay, so we've been looking at starting to look at dynamics before the break. We looked at non-renewable resources and how we do dynamic optimization for non-renewable resources, and that's probably the most straightforward dynamic optimization problem. Today I'd like to start looking at renewable resources, and in particular we're going to focus on the fishery problem, and the fishery problem is yeah, it's being recorded.
Okay.
Yeah, so we're going to the fisheries problem is an interesting one because, well, it's a renewable resource, but it also links biology to economics and the biological structure of populations and how they interact with fishing efforts is key to understanding fisheries economics. With fisheries, then you can focus actually on 2 solutions. One relatively straightforward solution, which is called the steady state, and that gives the fishery in equilibrium, and you can look at how the fishery changes as the parameters change, and it's going from one equilibrium state into another equilibrium state. And I suppose that was probably how most fisheries economics was done back in the 1950s, 1960s. More recently, then there's been, I suppose, a bit of a revolution in fisheries economics, and it tends to look at dynamics, which is relationships through time, and how you get from where a fishery is now towards the steady state, and then possibly away from the steady state. And the problem with that dynamic process is it's a good deal more complicated. But I'll tell you something about how you can analyze that using mathematical programming. The only challenge is that the mathematical programming problems become very large, because if you have 20 periods, then you have to represent stock variables, catch variables, and effort variables for every single period. So you've got 20 times, three variables, so 60 variables immediately. You have to try and solve for. Okay, so I'd just like you to open up from it's actually from the lecture slides. So YouTube, lectures, PowerPoint, and NP, and it's actually under week 16, and then there's there's the file that we've used previously. It's been updated, and in fact it should have been a bit more updated, but I was probably sharing some of your pain with Mathematica. I did a day's work on it and lost it all because Mathematica crashed. So this version is possibly not as polished as it should be, and it might improve a bit further. Okay, so if you open that up, then at the top there's the stuff we've gone through already, which is about the general structure of dynamic problems, and we looked at the Riker curve and how you can have very complex difference equations that give these unusual relations patterns through time. Something about discounting, and then we went through the. I'll make this a bit bigger in a second. And then we went through how to solve the non-renewable resource problem. So that's going to appear in numerical problem 3. And then if you scroll down, we looked at the idea of comparative dynamics. So with a non-renewable resource, is there a steady state? Does a steady state make any sense with a mine? So with a mine is never going to be in a steady state because it's always changing. As soon as ore is extracted, then the situation of the mine changes. So with mining, there's no possibility of a steady state, and then here we start to look at fisheries economics. So we're going to look at fisheries economics in discrete time. So we're just looking at using a difference equation to represent the stock, and we start off in this introduction looking at the traditional fisheries economics and fisheries biology model of the 1950s, which is called the Gordon-Schaefer model, and that was all about analysing fisheries using the steady state, and they defined something called the yield effort curve, which is a relationship between the catch of fish and the amount of fishing effort that goes into the fishery. So if you just scroll down here and just make sure that this block of parameters are defined, and I've just I changed the code. So if you could just change the code, I'll fix this up later. But if you see gamma, then just type in gamma as a word, because I tried to remove the Greek letters because they just cause confusion. So if you just make sure that these parameters are all evaluated, then you can start off by generating So this equation gives the growth curve that's used in the Gordon-Schaefer model, which is just the logistic. Plot out the growth curve as a function of the stock, and it gives you a steady state K, where that's the carrying capacity of the stock, and it's basically the biomass of fish if the stock is unexploited. If we just so if we just scroll down a bit further, then we use some commands. We use the eliminate command here, and what that does is it allows us to take a system of equations. So in this case, the equations are the catch function here, which is a function of the fishing effort and the stock, and it allows us to solve that system of equations, eliminating one of the variables. So in this case, the variable that we want to eliminate is actually the stock. So that means that we can use the steady state. So the steady state of the fishery is where the catch is equal to the growth. So the growth is given by this logistic function here. We've got a catch there. We want to solve for these equations, but at the same time we want to eliminate the stock. And the reason we want to do that is we want to have a relationship between the fishing effort and the catch. And so we've effectively got it so that we're just looking at we're looking at it from an economic perspective. So that the effort is a measure of the input into fishing in terms of trawler days or some other measure of effort, and Q is the catch of fish in tons. Okay, and actually in economic terms, that's a production function. There's a relationship between inputs and outputs. The next step is that we want to convert this into an economic relationship. So what we do is we multiply the catch of fish by the price of fish. So the price per ton of fish. We multiply the fishing effort by the cost of fishing effort, and that gives us a total cost. And then we subtract the total revenue, so the price times the yield less the total cost, so that's the cost of fishing effort times the fishing effort, and then we can hopefully try and just check that this actually works. So some of it does, some of it doesn't. I've failed to define a couple of things up here, so I think if I now, yeah, so just make sure that everything is defined, then you should get a diagram like this. So you have total revenue, total cost. What you're looking for is the biggest difference. If you're managing a fishery, the biggest difference between total revenue and total cost. So that's between these two lines here, and where you find that point, then the profit is maximised. Okay. Okay, so that's up to there is fisheries economics, 1950s, 1960s, based around the static model of fishing and based around the yield effort curve. Okay. Now, when we did non-renewable resources, then I said you could solve the profit maximising problem for a mine using Lagrange multipliers. All right, we used N-maximise just to make life easy. But the Lagrange multipliers are informative because they tell you how much a ton of ore is worth in the ground. Exactly the same principle applies to fisheries economics. And the Lagrange multiplier is just measuring the value of fish in the sea. All right, so it tells you how much an extra ton of fishery biomass is worth in the sea. Why do we want to keep fish in the sea? Well, there's two reasons. They maintain the biological growth rate of the fishery. So if you've only got two fish left, they probably won't even find each other. So you've got to try and maintain a stock of fish so that it maintains the growth rate of the fishery. And the other thing is, what happens to your costs of fishing if you have more fish rather than less fish? Is it going to be easier to catch fish if there's lots of them? Yeah. So if you've got lots of fish, you're spending less time chasing around the ocean, burning off fuel, trying to find fish. So the other reason you want a high fish stock is because it makes fishing cheaper. Okay. So the way that we set this problem up as a mathematical programming problem is straightforward-ish, but some of the interpretations are a bit tricky, and certainly when it gets to looking at solutions through time, it becomes really quite difficult. So I'm going to gloss over some of the details, but I'll say what the principles are and give you what's called a golden rule of optimal fishing. And I'll explain how that can be used to solve for a steady state, and how it can be used to do sensitivity analysis on the fishery model. And then I'll go on and show you how you can do the dynamic analysis, but you leave mathematical programming to take the pain, because quite often the algebraic solution is just impossible. All right. So fisheries economics using Lagrange multipliers. So I'll just make this a bit bigger so the people at the back stand some chance of seeing. Okay. So we have a Lagrange composite function, but we also have this summation because we have to look at we have to look at this problem over time. And in fisheries economics, they say that the end of time is infinity. Well, that's a bit problematic because you have to, if you're doing mathematical programming, you can't put in infinity because your software will just sort of collapse. You'd have an infinite number of variables, so that's not at all useful. So we have to have some end time when we stop fishing. So you can usually just say, well, let's run it for 20 years or let's run it for 30 years, something like that. You want to sum the profit up. So I use pi here to indicate profit. So you've got a profit function, and profit is a function of the stock of fish and the quantity of fish. And the reason it's a function of the stock of fish is because having more fish makes fishing cheaper per ton caught, and therefore increases profitability. So we've got profit function. We've got a discount factor here, which is DT. So that's just giving the value of $1 at a particular point in time. Again, we've really just got one type of constraint, which is simply that you can't catch fish that you don't have. So it's just saying that the catch of fish and this profit relationship is governed by the fishery growth function. And that fishery growth function is included. It's a difference equation, and it's included. If you were to interpret what this means, it says, in fact, it's interpreted down here, that xt plus 1 minus xt, so that's the change in the stock of fish, is equal to the growth, and then adjusted for the harvesting. So adjusted for any harvesting that goes on. Okay, and then this lambda t here is the Lagrangian multiplier, but you have to have why the t. You have to have the Lagrange multiplier for each period. So yeah, this constraint doesn't just apply in the first period. It doesn't just apply in the last period. It applies at each period across the planning horizon for this fishery, going from time 1 through to time 2. How do you solve this? You go back to first principles, take partial derivatives with respect to the stock, with respect to the catch, and with respect to the Lagrange multipliers, which just gives you your constraint back. So same principles as we've already applied. The only difference is that you have lots of these Lagrange multipliers. So it gets a bit nasty, to be honest. So if you have 20 periods that you're going to solve this over, you've got slightly less than 20, sort of 18 of those, 20 of those, 90 of those. So nasty problem. You wouldn't want to solve that. It's impossible to solve by hand. So. Now, we were talking sort of first week of semesters about the space race, and Richard Bellman and Pontryagin. She's probably forgotten, but it was about there were two schools of analysis related to the mathematics of dynamic optimization. So one was the Russian school under Pontryagin, and the other was the American school under Richard Bellman, both trying to get rockets into space and minimising the cost of minimising the quantity of fuel required to get a rocket to the moon. All right, we're going with the Russian solution. Okay, so this is Pontryagin's approach, and it makes more sense for economics. Because all these partial derivatives are really hard to remember, then what Pontryagin did was he defined this other function, which is called a Hamiltonian, and he boiled it down to being just two conditions. One is called the co-state condition, which we're not going to worry about too much because it's quite hard to interpret. But the other one is called the Hamiltonian condition, which has a straightforward interpretation. So we're going to end up with a solution that uses these approaches. Okay. So I just like to focus on this. So we've defined a profit function here. So that's just the total revenue, and then this term here you can just think about as giving the total cost. So the profit is just total revenue minus total cost, and then we've got the growth. We've got the growth function here, and this gives us the change in stock. So it's giving us a change in stock, and we're defining the Hamiltonian. So we define this function, and all this function does is it just helps us to remember all those conditions on the Grom's multipliers and partial derivatives. Okay. Right. So you might want to just make sure these things here are defined. And then we're just going to define some derivatives here. So that's the derivative with respect to the catch. And then the next one is the derivative with respect to the stock. And I'll just have a look at one of those and explain how it's interpreted. Okay. So if you just perhaps just pull out this one here, HamQ, and just have a look at it. And you might want to just make sure if just clear that lot. Okay. Yeah, I might just have to clear the numbers and just look at. Okay. So the Hamiltonian condition, which is set equal to 0, what that does, if we just write it out as we have it there. So you've got 1 plus Uh, so let's just simplify that. So 1 plus R. So that's just this term here is just the discount factor. Multiplied by this is the extra or marginal profit. So this is the extra profit from catching a ton of fish. So taken all together, that just gives you the present value of catching a ton of fish. And then you've got this Lagrange multiplier here. And so we're going to set this equal to 0. So therefore, we can put that Lagrange multiplier over onto the right-hand side. And what this does is it gives you a very simple rule for doing dynamic optimization. And what it says is you should carry on catching fish up to the point where the value of an extra ton of fish is just equal to the value of leaving the fish in the sea. So that's how you do dynamics. You've got to look to the future. Okay, so you carry on catching fish now, and you get this value here. It has to be equated with the fact that those fish have a value in terms of leaving them in the sea, so that they can produce more fish and also continue to reduce costs of fishing into the future. So that at the guts of it is what dynamic optimization is about. You take a decision now which increases your profit, but you're aware that by depleting the fish now, you're reducing profitability in the future. And what accounts for that? It's the Lagrange multiplier. So the Lagrange multipliers account for the fact that fish have a value in the future. Okay. I'm not going to go through the algebra of this because it's a bit tedious. But if we just evaluate that, then just make that a little bit, try and make it a bit bigger. What you end up doing is you solve for the co-state and the Hamiltonian condition, so you get the optimal level of catch and the optimal level of stock is related to the discount rate. So why is that the case? Well, this model treats fish in the sea as capital. So what it's describing here is an equilibrium between holding money in the bank, that you catch a fish and you put your money in the bank, and that earns interest. But you have an equilibrium between holding money in the bank and holding sort of money in the sea, which is in the form of fish stock. So that's why we have this relationship here. R is equal to these two terms. So what are these two terms? Well, this term here is accounting for the fact if you hold that last ton of fish in the sea, it's increasing the growth rate of fish. So it's giving you more fish in the future. So that's this term here, which is the derivative of the growth rate. And then there's this term here, which is accounting for the reduction in cost. And that's probably the best way to think of it. Two terms. One is the ability of stock to support growth, and the other is the ability of stock to reduce costs. And that's probably all you need to know. Okay. So let's look at this for a numerical example and derive the steady state. So what I've got here is a collection of parameter values. In the version I lost, I've changed all my features, but we'll leave it with feature at the moment. All right, so these are parameter values for a fishery, and we're just going to use nsolve to find the optimal steady state, and we've got this term here, R, and what that's doing is with it's actually giving us it's giving us this equation here, but it now looks a bit more complicated because you've got all the specific functional forms. So if you just evaluate these parameters, and you're defining a function here, and then you're just using nsolve, and things seem to have worked out okay. And you get the optimal captured fish, which is 72.986, and you get the optimal stock of fish. And this solution is for a steady state. So that's convenient because we can forget about all the time subscripts. We're just getting one answer to the fishery. Okay. Now, numerical problem 3, you'll be asked to do some sensitivity analysis on this. And one parameter that is key to dynamics is the discount rate. All right, so if I reduce the discount rate to 0, what do you think would happen to the optimal capture? Would it go up or would it go down? Okay, so we just need to set the discount rate to 0. I just resolve that. Then the captures increase and the stock has also increased. I'll just also set the cost of effort to 0. So you just try that. If you have both the discount rate and the cost equal to 0, then you get the biological solution, optimal fishing solution, the maximum sustainable yield. So I just do a quick diagram of what's going on. So we've got growth in this fishery at the moment. Then the carrying capacity is 1,000. The maximum sustainable yield, because of the functional formula we've used, is always 500. And so that's given us a stock of 500, and in that case, it gives us a catch of 75 is sustainable. If we increase the discount rates to say 10% and reevaluate, then you see that the catch and the stock have gone down. So if you increase the discount rate, then you tend to get the stock and the catch coming down. What if I increase the cost of fishing? What is that going to increase or reduce the stock? Reduce the stock. Cost. Increase the stock. All right, so let's just explore that. At the moment we've got 0 stock, so let's make that, I don't know, 10, something like that. So that increases the stock, and in fact, if you increase it to 100, which is quite extreme, there's no solution. If you increase it to 100, there's no point going fishing. So that doesn't work. But we've gone too far. So 30. Yeah. So if you in this case, you can actually, if the costs are high enough, you can actually push the stock beyond the maximum sustainable yield. And optimization is doing that to reduce the cost of fishing. So as the discount rate goes up, then holding everything else equal, then the stock comes down. If the cost of fishing goes up, then the stock of fish, optimal stock of fish, goes up. So these are the optimal values. All right. So you're required to just analyze this model for numerical problem 3. I'm not requiring you to do dynamic optimization, but before I finish, I'll just show you some dynamic optimization. So this is the next bit of code. If you analyze that, if we get lucky, it's a bit hard to see the solution here. We started off here at an initial stock of 600, and what's happened is that there's the time path for this stock shoots very quickly towards the steady state. And so this is not a fantastic example. The example I'm using here is not a fantastic example of comparative or of doing dynamics, because it's a bit boring. So what happens is it just starts there, shoots there, jumps around on the same point for quite a number of periods, and then towards the end it will diverge off to whatever I've set the terminal condition. So in this case, if you look at the detail of the code, then I've included a restriction that the stock can't go less than 350. So if you give it enough time, it will hit 350. So the thing with dynamics is you're starting at a point that you set, and then you're defining a point where you end up at. All right, I just like to absolutely finish off looking at a slightly more complicated model. So all I've done here is I've added more. I've made the cost function increase more rapidly as the catch increases. So I just added another parameter. But this gives slightly more interesting dynamics. So you start off at 600 and you have a harvest level which is around about 90. This red line here is giving you the growth function, and this neon green dot here gives you the steady state. What happens is if you look at so you're starting here and you're going through lots of solutions over 20 periods. What you'll tend to see is that the solution heads towards a steady state and then diverges away from it, depending on what the final condition is. Because in these models, it's usually the case that implicitly the fishery isn't worth anything at the end point. So that then means that you're going to ramp up. You're going to ramp up your catch as you approach the end of the period. If you made the period, say, 100 years, then you see the solution getting closer to this steady state, and then only diverging away towards the very end. So this is an example of what we did with the non-renewable problem, which is looking at comparative dynamics. But you'll be pleased to know that you don't have to do this in numerical problem 3. We're concentrating on Monte Carlo simulation, which is even more dastardly.
Can I get you to go to with 18 and 20? And if you scroll down, then you'll find the mathematical code. ENVT topic 9 and 10 version 1, I think. Yeah, everybody. So we have covered this basic structure of this lottery system in the class this morning. In case you have missed it, we have, so this protocol or the system that has been designed by the experimentalists who were interested to know about the risk attitude of people. And the way they set it up is that there are a series of gambles, and decision makers have to make a choice from, or in this case, in the individual respondent have to make a choice for each policy. So in this gamble, these are a set of gambles from gamble number 1 to gamble number 10. I'm not sure whether you can see clearly from the back. Can you see from the back? Or you can look at your screen as well. You don't have to. So in gamble number 1, there is a probability, a 10% chance of getting $2 outcome, and whereas or 90% chance of getting $1.6. Versus this option B, where you have a 10% chance of getting $3.85 versus 90% chance of getting $0.1. So, and then if you scroll down, what you can see is the payment for the payoff or the outcome is always the same. Is the $2 and $1.6, $3.85 for option B, and 10 cents. But what is changing here is the probability of getting this low and high outcome, each of these. Yeah. So what we are interested to know your choices for each of these gambles. So from 1 to 10. So one way to look at it is that to make it easier, if we go back, scroll down, so where we have multiplied it by 50 just to make it a little easier instead of using the original numbers that was used by the authors. We have multiplied all the numbers by 50. So we have gamble 1 again, so we have 10% chance of getting $100 and 90% chance of getting $80. So that's our option A. And option B is 10% chance of getting $190 and 90% chance of getting $5. So if we are given this gamble 1, which option we will pick? Will we pick option A or option B? That's the choice. So this is just a setup. It's just everything, and all the numbers have been multiplied by 50, and we're seeing all the gambles. One thing is interesting to note here is that in gamble 10, we have 100% chance of getting $100 and 0% chance of getting $80 and 100% chance of getting $190 and 0% chance of getting $5. So this is a certain payment. So we also have covered utility function and how this risk attitudes or risk aversion parameters are incorporated in utility functions. So let's imagine that we have an individual or a decision maker whose utility function is given by this here. So x to the power 1 minus relative risk aversion parameter. X to the power 1 minus RRA. Now we have a function, and then what we can do is that if you remember, we are talking about certainty equivalence, and that's something we'll look into more details. So let's first look at the graph itself, then we can come back to the mathematics. So we are talking now about only a single gamble, right? And then we are saying that there's a chance of getting either $190 payment or a chance of getting a $5 payment. And what we can calculate the expected values of the lottery, of the gamble, and then we can also plug in a utility function for a risk averse decision maker or an individual. So what we get here, so the expected utility of any combination of 5 and 190 as given by the line AB, that's the straight line going from 5 to 190 and with the utility on this axis. And so in this case, the expected utility for this particular lottery, which is 90% chance of getting $5 and 10% chance of $190, the expected utility is plotting in the income as given at point C. So that is the point here. Yeah. And then we can also calculate the expected net income, which is point here, which is around 53 point something. Now, okay, let me draw it here so that when I move, I can refer to this. So this is my $5. This is my 190. So this is like this. And then what I'm saying here is that this point here, and then what we need probably another color. So we have this. So this is 190. This is fine. And then we say that our what is our expected utility is somewhere here. And then okay, let's check the code. So the point C, which was this point here, is for a risk neutral individual. Oh, this one working at all. So this is our risk neutral and this is our risk averse. So point C is the expected utility for or in this case, this is also the expected outcome of a risk neutral bidder. And then if we draw a line like this, which would intersect here, so that's our point E. And if we draw a line like down here, so that would give us their risk premium, the difference between these 2 points. So they have E as well. So E is the point where it has crossed the line. This, yes, the line and the curve, which is EC. So EC is our risk premium. Yeah. Yeah. And C, sorry, not C, E is our certainty equivalent. So obviously, a risk averse individual is paying or valuing less of the lottery compared to a risk neutral individual. So you can imagine that this difference is something that a risk averse individual is willing to pay to buy protection against the loss. You can imagine that way. It's like an insurance. Does it make sense? Okay, the code should work. I would encourage you to try to see if you can generate the graphs. So the relevant code is given here, where it's just is for lottery. And let me know if it doesn't work. Yeah. So that should be pretty straightforward. Then let's go back to more details. Now we are going back to the survey again. We're saying that imagine these are 10 gambles, and this is a survey-based method. So we ask individual respondent, okay, what is your option? Do you pick option A or option B for each of the choices or gamble? So what we want to know is that first of all, how the expected utility will be different between these two options, like option A and option B. So here, this is the expected monetary value for lottery A and lottery B. You can estimate yourself as well. But basically, it's in the slides that I presented the difference in expected values. But here you can compare yourself. For example, in lottery A, gamble A, we have an expected monetary value from lottery A is $82, whereas the expected monetary value from lottery B is only $23.5. If we go down, then we have here gamble number 10, we have this 100 and 190. That's the third one. but you can see that the relative difference is changing as you move along through the gamble. And it is pretty clear like how this has been set up. So we have 10 gambles, so 10 probabilities. So going from 1 to 10, like at a 0.1 step. Then we are saying that there are four payments, payment 1, 2, and 3, and 4. That's pretty obvious from the tables, etc. And then basically calculation of the expected monetary value calculation. So there's the probability multi times payment 1 plus 1 minus probability times payment 2. And similarly, we can do it for payment 3 and payment 4. Now let's have a look at just one payment and then see what is the chances of, if we vary the risk attitude, how the utility is different. So here we have picked up just 4 numbers. So we are plotting the utility difference, but we are interested to know the changes in the utility difference with respect to their risk attitude. And so the difference is A minus B, if you remember, option A minus option B. And what was the payment here on option A? That was 180, right? And for option B was 190. So the risk attitude we are varying from -2 to 1, and this is how the utility is changing. Yeah. We want to have a go and see if we can generate the plot and maybe change some numbers to see the utility, the difference curve is changing or not. So this is risk attitude and the other one is the utility difference. Okay. So we have this x to the power 1 minus r, yeah? And then we calculate the expected utility, and then we're taking the difference. So this is given here in this equation here. If you look at carefully, so you have probability times payment, and that payment is x to the power 1 minus r on a, so that's the utility function. And then we have 1 minus probability 1 times payment 2. So payment 1 and payment 2 are related to option A, right? So that's in total the expected utility from option A. And then we are subtracting expected utility from option B, which is probability times payment 3 to the power 1 minus r plus 1 minus probability times payment 4 times 1 minus to the power 1 minus r. Okay. So the equation is given. Okay, what does it tell us about the impact of risk attitude? These are highly risk averse. The smaller the number is, the risk averse they are. Whereas these are more risk seeking, risk neutral risk seeking. Is there any difference? Like if somebody has let's say that value of risk attitude value of 0.5, is there any difference between these two options in terms of expected utility? No, it's zero. So there's the difference, right? And then like it's the so this is and then but as they become more and more risk averse, they would prefer to have select which option? Option A, which is the safer option. And we can see it from because the difference is positive now. So that is risk is not risk difference. If somebody has a value here, yeah, they are risk averse. But why would you do it? So the less risk I take, the more money I get. No, it's the utility. So option A is the safer option. Okay, and what we are estimating here is the difference in utility. So utility, say expected utility, I should say expected utility from option A minus expected utility from option B. Yeah. So here, if somebody is risk averse, they are getting more utility from selecting option A. That's what it's telling. Whereas if somebody is here, they are indifferent because there's no difference between this. Okay, so we can estimate, we can take the original 10 numbers and then we can estimate people's risk attitude. But what I just want to show you is the point of indifference between lottery A and lottery B. So this is what if somebody was to select, let's say this is the point of indifference is when we this difference expected utility from option A and minus the expected utility of option B would be 0. So we are trying to estimate which value of risk aversion attitude would make the expected utility from these two options the same. That's what we are trying to find out. Yeah. So if I go back here, let's take one solution, one lottery. So we are just solving equation number 1 here. So this is option A. Remember, this is option B. We are calculating trying to find the root, which means that the difference here it would give us equal to 0. So the expected utility and from selecting option A and expected utility from selecting option B. Okay. That's what we were saying that. Sorry? Well, if say that we have A is a safer option. Okay. So when would I select option B? If I am slightly more risky, because A is always safe, but I'm selecting option B. Why would I select option B? Because it's giving me some happiness, that's fine. But at the same time, I am also a bit of risky. So at which point I would have the expected utility from option B is equal to option A. That's the risk attitude parameter that we are interested in. So it's the limit at which we'll get the risk attitude. The utility of this would be different, same, and that would give us the risk attitude. So let's.
So you want to have a risk attitude when the results of the project are the same?
When the expected utility from both lotteries are the same. The lotteries, the real expected values are different. Is that which person would select an option B compared to option A? That's what you want to understand, and that's why the risk attitudes are changing. So if I so here it gives a sensible thing. So here is for every lottery A to B to T. So what we are saying is that if you choose lottery 1A and then choose lottery 2B, your risk attitude is between a range of minus 1.75 to 0.97. It's always the limit. That's what we are trying to find. So here is how do we do it. So for each of the lottery, we are trying to find that which value of RA would give set both expected utility from option A and option B equal to 0. And that's how we calculate for each of these. So if somebody, imagine that if as I've showed in my slides, that I have started from A, and then let's imagine that I have switched to option B. So option B is a riskier option. So what does it tell about my risk attitude? So here option for lottery A, I have selected option A, and I'm risk averse. Here I've selected option A, I'm still risk averse. Here I have selected option. Did I say 3 years? Okay. I have selected again option A, so I'm risk averse. Here I have selected option B. So I have gone for a more riskier option. So my risk attitude is somewhere between minus 0.1 to minus 0.16. So this is the point where I'm switching from option A to option B, more riskier option. Does it make sense? Am I making sense or not really? No? Again, okay. It's all right. So let's take the first lottery where we have 0.9. So this is times 5 to the power r. Okay, so I'll go back to the original one because Ben has slightly different way. Okay, this might be better. So I have 0.1 times 100 to the power 1 minus r plus 0.9 times 80 to the power 1 minus r. So that's my expected utility from option A on lottery 1. For lottery B, sorry, option B in lottery 1 is I have 0.1 times 190 to the power 1 minus r plus 0.9 times 5 to the power 1 minus r. So obviously we have seen that the expected utility is higher for lottery 1. So expected utility is greater than, sorry, not the expected utility, is the payoff. So we want to know, so this is less, this is safer option. Why I'm saying safer? Because if you look at the payoff, $100 and $80, there is not much difference. The probabilities are the same. Whereas here, you have $190 and $5. The payoff is the difference is much larger. So that's why it's more riskier. Yeah? Clear? Okay. So which person would go for selecting option B? Right? If somebody is more risk seeking, like it's a relative term, it's not like it's absolutely risk seeking. So what we can say is that in order to get somebody to select option B, what should be my value of risk attitude? That's what we want to know. So here we have utility from option A. Only thing unknown here is R, right? Everything else is given. Here again we have for the same person utility from option B. What we are interested to know, at which point, like at which value of R, this person, instead of selecting option A, would select option B. That's the point that we are estimating. Yeah? Now makes sense? So if we equate the expected utility of these two for these two choices, that we can get the value of R, the risk attitude. I have to be more risk seeking to select option B in lottery A, right? Lottery one. Now if we can iterate for each of the gamble, and that would tell me at which point I switch from option A to option B. At some point I should switch to option B because it doesn't make sense to go continue option A. So that's what we are doing here, and we can saw, okay, now that's the certainty covenant part. So here we are calculating the expected monetary value. That's fine. It tells us that we are likely to get higher values from lottery B after a certain point, which is I think around number 5, and then yeah. Why would I want the level of risk? Very good one. And this also leads to the second part. If you imagine that you are a manager, okay, and you are trying to implement a project, you have a chance that the project could generate good benefit to the community, or there might be some risk of failure. Would the community accept it, that project? Would they say that why you have selected this project? Yeah. So that's why the risk aversion information about risk aversion comes into place. Now think of, you have two projects. One is less risky, less profitable. Another one is more risky, more profitable. Now in this time you are an investor, okay, not a commercial investor, not for the community. Which one you would pick? Would you go for the more profitable but more risky project, or less profitable and less risky project? Right. So that's the gamble that we are seeing there is showing that kind of dynamics. Even though we have kept the payment fees, but we have changed the probabilities. That means the expected payoffs are changing. So, and you can answer yourself that would you go for a less risky or more risky project? And that would tell you how risk averse you are. Yeah. Now, if somebody asks you like, okay, why would you go for? Let's imagine that I would say I selected less profit and less risky project, and then my shareholders ask me, why did you select this project? Why didn't you go for that one? Right. So that's when I have to explain that because of all these variables and because of in order to protect myself against loss, I have selected a less risky one. So that's another place where information like this are useful. And then you can also think of another, especially if you are in the space where there are chance of catastrophic disasters, or you are in a very like environmental disaster management or these kind of situations. If there is a very low probability of having very extensive, very severe damage of something, it could be fire, it could be flood, and that could depend on how you are operating your dams or how you are operating your infrastructure. Very low chance of having very high risk, very low chance of getting very severe damage, right? But most of the time it's fine. Versus you have another operation or manual like procedure, which would give you like will minimize the risk in such a way that you have low chance of having severe risk, but you have moderate chance of getting moderate risk. Like, so these are various possibilities, right, in terms of risk and uncertainty. As a decision maker, as a policy maker, as the CEO, which project you give the signal to? Yeah. That's where again it's helpful to understand like, okay, what we are responding to we are not like in the real world, we are not estimating this kind of like utility function when we are making decisions. But these risk, uncertainty, these will always come into play, like when you are doing modeling of calculation. Yeah? All right. And then let's quickly go through this part. We have covered in the slides as well as in this class, but these are just the mathematical codes that Ben has used. This is simply two distribution of income. You don't have to imagine that it's an income. If you're more biologically oriented, this could be your um, number of animals that you have protected, the stock size, could be your any biological parameter that you are interested in. It could be an environmental target again. It could be your water quality measures. Right? But whatever that is, imagine that you have two projects again. It's about selection. It's about and the blue one gives us a distribution of income. Let's go with income of so it has $100 as the mean, and the standard deviation is the same is the $10. Whereas the orange one has a standard mean of 120. So that's why it has shifted. Right. And then a standard deviation of $10. So this is our prospectus. Which one we would pick? Now we have spoken a lot about these utility functions, but so which one we should which utility function we should use? That's the subjective decision. Whose decision should matter most? Is the community or is the policymakers or the managers utility? This question attitude, that's again a subject of discussion. So there are lots of uncertainties. So the one way the analysts have developed a procedure to think about this kind of problem where we have to select a project or an activity just based on their empirical distribution of the expected outcome. Yeah. So here are two distributions, and the concept that we are using is the stochastic dominance concept. So we are going for only the first two dominance criteria. One is the first order, and then the second one is the second order. So we have a distribution like this, probability distribution. So the second thing we should do is the cumulative probability distribution. We should draw that. And the codes are there, so you can try if it's working or not. But what even essentially you get is what is the chance of getting a certain amount of income or lower than that certain amount for these two distributions, like blue and orange, G of x and f of x. So one is clearly dominating the other, right? So we have discussed in the class, but those who are not in the class, what we are seeing here, for example, with the blue one, we have a high chance of getting low income compared to the orange one. Yeah. So that's what we're saying, that the blue one is on the left of the orange one, and there is a clear separability between these two distributions. According to the first order stochastic dominance criteria, the one on the right, if it is a clear distribution like this, would dominate the other one. So just to show you the concept here, okay, no, not this one. Did I miss? Okay, just to show you the concept more clearly. Again, this is cumulative probability distribution. What is the probability of getting $100 or less under these two probability distributions? In the case of blue one, that's somewhere here, whereas with orange one, it's very low. So let me ask you, which one you would pick, like given this kind of distribution? Orange or the blue one? Blue one. Orange. That's because 100 is just a number, but you could have like 150, 200, right? This is just a number. Yeah. So this cumulative probability distribution is telling us what is the probability of having $100 or less, not more. So which means I have a very low chance of getting $100 or less from the orange one. But on the other hand, with the blue one, I have a very high chance of getting $100 or less. So that's why the orange one is dominating the blue one. Okay? So there's a bit of text to just explain what I've just mentioned. But what is more interesting in the last few minutes I want to cover is this one, where you have a situation like this, where there is no clear dominance. Is it, for example, here you have more chance of getting a like say $60 or $70 with the blue one compared to an orange one. Here, so this is where this orange one is dominates, but here you have this blue one. So there is an intersection, and there is no clear separability between these two distributions. How do we build them? Which option we should select? We have to go for the second order stochastic dominance. So what we can do, we can calculate the integral of these two distributions over a certain range, and we pick the one which has the smallest area or the smallest number. So this is just visually is telling us that the orange one has a smaller number, but this could also be calculated like you can, if you give a certain range, you can calculate directly the amount, the area. So let me go back here. If you look at the, okay, let's start with orange one. The area under the orange curve, right? That's what we're interested in. That's what we're doing the integration. The area under the orange curve is this one. Whereas the area under the blue curve is this, and this. So this is common, right? So they have the same area here. But the blue one has big area here, whereas the orange one has area here. So the difference between these two determine which one has the smaller area. Okay, obviously the blue one has a smaller area. Sorry, blue one has the greater area because this area is bigger than that area. So that's why we are saying that the area, whichever distribution has a smaller area under the curve is our most preferred option. Yeah, the code should work all fine. Like if you want to try, but you can also let me know later if the codes are not working. But the concepts are more important in this case. Okay, the last bit is on the example that we have on the slides. It's just like instead of calculator, I just use mathematical codes to generate the number. But what you could try is you can try different probabilities and then see what happens to expected outcome. So this is we've said that there are costs and benefits, the best case, and then the probabilities of having different levels of guess, like low, best case, and high. Obviously, the best case is the one that we think are most likely to happen. So that has a probability of 60%, and the low and high have 20% possibility. So the best case, we think that our cost was $100 and the benefit was 145. Whereas with the low scenario, we have $50 as cost and $90 as benefit. But with the high scenario, we have $125 cost and $225 benefit. So given this distribution, if these are the rest are just set up, we're saying that cost low, medium, and high, benefit low, medium, and high. Then we calculate the joint probability. That's the multiplication of individual probabilities of. So joint probability of low cost and low benefit is probability of L times probability of L because they have the same probability. That's why we have used that. But you can change it. So we have these different scenarios. Then we are interested to know the L to estimate the benefits, and then that benefit there's a multiplication of the benefit times the joint probability, and then the expected monetary value. So if I just run it, should give me 55. That's also in the slide. And but now I would encourage you to change the probability is into instead of 0.6, maybe you change it to 0.5, but they have to sum up to 1. So we can say that this probability has low probability has 0.1. So we are more likely to get low income and low benefit. Sorry, low cost and low benefit. Would it change our net present value, expected value? It should, right? It should be low, you think? But the benefit is also getting lower, so I'm not sure. Let's see. Yes, you're right. So that now has become 37.2. So you can play with this, but at the same time you can also think of like a situation where maybe the benefits and costs are highly correlated. You can only get high benefit you are spending low, or maybe you can only get low if you are spending very little, you are getting only low benefit. You're not going to get high benefits. So these kind of relationships could happen. So yeah, do you have any questions? That's what I wanted to cover. There will be a few questions, and I think Ben has already opened ENVT. I'm not sure. There will be questions on stochastic governance, maybe something similar to this. You can tidy up. You can put it as a table instead of just having these codes like this very linear. All right. See you next time in the seminar, and then also another lecture on that.
Sir, I how did you justice what? Is that what he meant? Like